Okay, so there is nothing hard in here. Well, you just write out what the linear combination is. So U is this guy, V is this guy. You write it in here. You use the bilinearity to express this in terms of the covariances of the xj's and, oh, that's a typo, yk's. Voila. It's good that I read this then. And then we're left with the gamma jk's, which give us this. Is that okay for everybody? I take that for a yes. Sorry, I'm just trying to get... okay, good. So then this is perhaps not the most efficient way of obtaining this result, although here it's very efficient. Another probably nicer way, so this means in my humble opinion, I prefer a more efficient way is to use matrices. So you should also be able to do this. So I write my guy here as, maybe I'll put some detail. So the sum of the AJXJ is just A1 to AM in line multiplied by X1 to XN in column. So that's all that this means. Same thing for the sum of the BJ's times the YJ's. So that we are looking at the covariance between A prime X and B prime Y. And here is a formula that you also should know, is that the covariance of, I don't know how to write it, A and B is what? Well, it's the expectation of A minus the mean of A times B minus the mean of B, except that this guy here is as a column vector, so there's a prime here. So this is a column, sorry, it's a line multiplied by a column. So now just using this, we are left with, I don't know if I have to add some detail. We obtain this result here, which says that the covariance between A prime X and B prime Y, well, maybe I should do it. That's what? Well, this is this guy here is a scalar. This guy here is a scalar. So this is the expectation of A prime X minus the mean of A prime X times B prime Y minus the mean of B prime Y. Like this. That's what? Well, that's the expectation of A prime times X minus the expectation of X times Y minus the expectation of Y prime times B. So here I cheat ever so slightly, and then I can take my A prime and B out. Of the expectations, and this is very precisely the covariance of X and Y. Is that okay for everybody?
Professor, the second line, when you say you cheat, what happens?
Here, okay. So that's something that those of you who have seen multivariate statistics, it's one of the games that's played very often. If I have u prime v, so u would be let's say 1 times m, and this would be an m times 1 vector. So this guy here is a 1 times 1. So he's of course equal to, because he's a scalar, he's equal to his own transpose. The transpose of a scalar is just the scalar himself. This is literally trivial because it's a scalar, and then we just apply the scalar. The transpose of a product is the product of the transposes in the other order. So that's what I did here. I have the u prime v here is v prime u here.
Okay, but I've seen that before. Like you have the u prime v or that prime transpose. So how come you just put the transpose without it being there before?
I don't get your question.
From the previous line above.
This one?
Yeah, it was So you factor out the b prime, something like that.
Yeah.
So okay, but what happens now, because from the trivia thing you said, yes, I understand, but there was no perfect. Yeah.
That's it.
Okay.
Okay?
Yeah, good.
So this trick of using the transpose is very, I mean, it appears all the time in multivariate statistics, and this way of writing a covariance is, well, in general, it's healthier to work with the matrix expressions than to work in coordinates, because working in coordinates can get very messy, whereas with the matrices it goes very quickly. So I would advise you to remember this kind of approach. It's okay for everybody?
Yeah.
Okay. So just wondering who's there. So there's 22 of you. So those of you who ask me questions, yeah, please interrupt whenever I don't answer your questions while I'm going through this. I'm thinking mainly of Clara? Was it you? I forget. Yes, Clara. So yes, so your questions were all very good. So please, I think everybody will learn from your questions. So if I don't answer them at the time when you're asking, if I don't answer them, just raise your hand and stop me. Okay? I think they were all very good. So second question. It's computing autocovariances. And we need to compute the autocovariance of weighted average of white noise like this. So again, it's the kind of stuff that if you don't know how to do it, then there's a problem, because you have to know how to do this. So if you're not at ease with this, please try it out, and if you don't see how to do it, how it works, call me, we arrange a meeting, I spend an hour explaining, but it must not be problematic for you at the end of this course. Do I need to do it in detail? I don't know. So WT is white noise. It means that its covariance is so its mean is 0 and the covariance is 0 off diagonal. That's the definition of white noise. So if VT is this guy, well, I choose to use this formula here in order to compute my covariance. So VT is can be written like this. That's okay, I suppose, for everybody. And then the covariance of VT with himself is what? Well, it's just I take the weights here, transposed, so as a line, multiplied by the covariance matrix of the guys whose linear combination I'm taking. So it's going to be the covariance matrix of t minus 1 with s minus 1 and so, well, like this. So it's going to be all these covariances here multiplied by the weights, but this time in a column, and then the weights are constant, and I have the 1 over 9. So is this first line okay? So this is just an application of this formula here. Okay, and now we have to work out what goes in here. So there's different cases. So depending on the value of t and s, well, not really depending on the value of t and s, but depending on the respective values, the difference between t and s, we will have different values. So the first case is when t is equal to s. In that case, well, this is just gamma 0, 0, gamma 0, 0, well, yeah, gamma ts, gamma ts, gamma ts. So it's just the covariance, where is it? Is it just the covariance at lag 0? So we have sigma squared, sigma squared, sigma squared, and all the other guys are 0 because the covariance of the diagonal is 0. So I think this is correct. That's okay for everybody? I guess so. If now s is t plus or minus 1, well then these guys will be 0. This guy will be 0, but these guys will be non-zero. So we'll have this guy here, which gives us this. And if s is t plus or minus 2, we get this. That's okay for everybody? I can only see a few faces, so feel free to shout if I don't react to your face. I put you on a big screen. There.
Sorry.
Yeah.
Just to be sure, the elements that are missing in the matrices, it's because they're symmetric, right?
Oh yeah, sorry. Yes, that's something I do. I'm a bit lazy, so I don't type them.
Okay.
Yeah, but the matrix is symmetric, so I just don't type what happens here. But yes, it's because it's symmetric. Okay, so then we, for free, get the covariance structure of this weighted average, which is this when so the covariance of Vs and Vt only depends on the difference between s and t. If this difference is 0, we get this. If this difference is 1 or minus 1, we get this. If this difference is 2 or minus 2, we get this. And if this distance is larger than 3, then we have a weighted average of covariance which are all 0. Therefore, we have 0. It's okay? Now, okay. The next one.
Professor?
Yeah.
Yeah, just to be sure, we used a different technique. I think the one you showed in class. I hope it's still correct.
Well, in class, we used the direct formula. So, but it will give the same result.
Yeah, it got the same result.
But it's just yeah. So here I'm just using this matrix formula, which is a bit handier. That's all.
Okay.
And then the next question, where is it? So now we have to take a linear combination. We have to look at the autocovariance of weighted average of the past t guys. Okay. So here, what I will again use the same formula. This one here. But so here now, this linear combination is just a mixture of the WTs, W1 to WT, with weights 1. So we have this expression here. And then what do we have? Well, maybe I should write it out. So exercise 2b. So xt is this. So now imagine that we have xt and we want to compare it with xs. So that's what? That's a comparison of, so without loss of generality, I suppose that s is less than t. So we have the covariance of 1 multiplied by w1 to ws, and then the covariance of 1. I'm gonna move this because I don't have enough room. So multiplied by w1 to ws plus 1 to wt. So here I have s ones. Here I have t times, and that will give me what? Well, it will give me a vector of ones. So I need what? It's going to be all ones and then zeros. Multiplied by the covariance matrix of W1 to WS and W1 to WT, multiplied by all ones in this case. Is this okay?
It is.
I don't get the zeros.
Well,
The left covariance in the left vector.
Well, we want to put it, so I think that's something I didn't discuss properly here. We want to put them in the, I think it's better here. We want to put them in the same dimensions, so we will see. So this
Yeah, okay.
This will be an what's it going to be? It's going to be an no. So there's no zeros. I'm wrong here. Sorry. I'm wrong. This guy here, I just have to be careful with my dimensions. So this guy here will be an S times T matrix. Is that correct? S lines and T columns. I think that's correct. So this is going to be 1 times 1 times S, and this is going to be T times 1. And then I don't make any mistakes. Is this good? So we have 1 to 1. And then we have what? Well, we have the covariance of W1 with W1, which is sigma squared. Then the covariance of W1 with anybody else, it's all zeros. And then we have the covariance of W2 with W1, which is 0, then like this. And then this will move all zeros, like this, all zeros, up to sigma squared. So I'll have a submatrix here, which is squared S times S. And then, sorry, I moved this. Where will I put this? I'll just delete it. And then I have the covariance of W1 with WS plus 1, which is 0, and so on. And I have all this. Strangely enough, I don't have the same thing as in the corrections, but maybe I was wrong in the corrections. Is this correct? So it's not a rhetorical question. I'm literally asking you, is this correct? And then I have ones like this. So I have 1 times S lines, T columns, and then T times 1. I have the impression that I made a mistake in my correction then. Or at least I have it in the wrong way. Does that look okay for everybody?
Sorry, why are there the zeros?
Well, the matrix here, it's the matrix gamma of ij is the covariance of wi with wj for I going from 1 to s and t going from 1 to and j going from 1 to t. So if I look at the first line, I have the covariance of w1 with w1, then w2, then ws, then ws plus 1, then wt. Here I have w2 with w1, w2 with w2, up to w2 with ws, then w2 with ws plus 1, and then so on. That's okay?
Yeah, it's okay, thank you.
So I think there's a mistake in my correction. Because here, so here what I did here was, in fact, it's the other way around. It's when s is larger than t. So I have to correct this. You all get that?
Yes.
Okay.
Yes.
So once again, when I ask you, is it correct? It's not rhetorical. It's, I mean, I'm literally asking you, do you agree? I wrote these corrections last year, typically between 1 and 3 in the morning, so I wouldn't trust them with my life at all. So I think we agree here, and now we just have to make this computation, so that should be doable. So I have my ones, and then I have the sum. Well, yeah, so I have this times this, it just gives you the sum each time. So I have sigma squared. Oops, sorry. I have a sigma squared. So I have a vector of sigma squares. So I have a vector of ones multiplied by sigma squared. That's okay. And this gives me what? It gives me s times sigma squared. So if s is smaller than t, I have s times sigma squared. And if s is larger than t, well, then the other argument will just give me t times sigma squared, so that I have the minimum of st times sigma squared. So I agreed I agree with the final answer. I just made a small mistake here. Everybody's happy?
Yeah.
But Professor, you said that was there you're considering s is greater than t in the, so it's just still correct, right?
Well, if I correct here, but so if I correct here, then it's correct.
Okay.
But as I wrote it, it's not correct, or at least I don't think so. At least today, now I have the impression that what I'm saying here is correct. I'm pretty convinced. So I think it's the other way around.
Okay.
Clara, you agree?
Yeah, I think so, yeah.
Okay. Good. So that's question 2 settled. Any questions? Okay, so let's move to question 3. Question 3, well, yeah, maybe I should have removed it because I was I removed that theorem from the course. But then again, this one is quite easy to show, so it's not a bad thing to have it in the exercises. So we have an independent sequence of random variables. It means that all the sub-collections have joint distribution which factorizes into the product of the marginal distributions. So this is the joint distribution factorizes into the product of the marginal distributions. And the question is, if we're given a sequence of independent distributions, can we guarantee that there exists a sequence, a stochastic process which has these given marginal distributions which are pre-assigned? And the answer is, well, basically it's immediate from the Kolmogorov theorem, because from the Kolmogorov theorem says that you have to check whether the family of distributions, so the family of finite dimensional distributions, actually defines satisfies Kolmogorov's condition. And the Kolmogorov condition is simply that whenever you let any of the components go to infinity, then the limiting result is just the initial FDD evaluated at whatever component you let to go to infinity, it has to disappear in the limit. So here we just can do this quite. It's quite immediate. The product here from 1 to n is you get out the ith component, this guy, and you're left with the product without the ith component. Now if you let xi go to infinity, well, this goes to 0, this goes to 1, sorry, this goes to 1, because this thing here is a CDF. And if you look at the limit then, well, the limit as xi goes to infinity, it's exactly this guy, the red guy. But this is by definition the finite dimensional distribution evaluated at the vector t. So ti is what? Ti is t1 to ti minus 1, ti plus 1 up to td. That's okay? It's not particularly exciting, but it shows that you can always define a stochastic process. You can always define an IID, an independent stochastic process. Okay, the next question is much more interesting. Did you try it out? This one, question 4.
I personally didn't.
Damian, you didn't. Those of you who didn't try it out, I'm going to ruin the surprise because it's surprisingly hard. I don't know if so. It's surprisingly hard. At least I find it hard. It's hard. I mean, it's. So you might remember so yeah, those of you who didn't try it out, well, maybe you wanted to leave the chat and come back in half an hour so that I don't ruin your surprise. If you stay, I mean, spoiler alert, you're going to lose part of the fun. Clara, I count on you. I think it's here that you had a question. I think I understood your question, but not sure. So please ask it again. So you might remember from the course notes, if I give you a stochastic process, its covariance function is even and non-negative definite. And the reverse question is, when is a function defined? So you take a function which is defined on the integers. Under what conditions is this function a covariance? Sorry, under what conditions is this function the covariance function of a stochastic process? And you might think that that's something that's only interesting for mathematicians, but it's not, because the whole point of this theory is to study functions and to apply what we know about functions to processes and therefore to real-life problems. And it is very useful to be able to just look at a function, study this function, and then say things about the process which is underlying this function. So of course, before doing this, you have to guarantee that what you're looking at is indeed the autocovariance of a stationary time series. And well, it's not easy to check. So let's look at the first example. So in order to check that a function is an autocovariance function, so once again I should correct this and put a v here and a v here. Well, there are two ways of doing it. The first way is to check that it is even and non-negative definite, and then we can appeal to one of the theorems in the course notes. And another way to do it is to construct a stationary process which has this function as autocovariance function. So is the game clear? Everybody understands what the point of the question we are trying to answer is? I take that for a yes.
Yes.
Okay, so the first one is just, it's a mise en bouche, it's quite easy. We take a function which is either 1 or 1 over h. And we want to know if that's the autocovariance function of something. Well, that function is, I seem to be doing a pun here, it's not even. F of 1 is 1, yes, and f of minus 1 is minus 1. Therefore, because it's not even, it cannot be the autocovariance function of somebody, because it's not, because if it were an autocovariance, it would be even. I'm pretty convinced by this. Okay, everybody seems convinced. Next one. We have the function here, so that function is what? So b f of h is minus 1 to the power absolute value of h. So if I write it out, if h is 0, I get 1. If h is plus or minus 1, I get minus 1. If h is plus or minus 2, I get 2. Sorry, I get 1, and so on. Okay? So this function is clearly even. I'll just get my course notes. Where are my course notes? Sorry, I'm just looking for the theorem. So we're applying theorem 1.38. So then the next, so in order to show that this is a covariance function, we need to, well, either show that it is even and non-negative definite, or we have to find a stochastic process which has this guy as covariance. So maybe I'll start with the second part. So well, if you're smart, or if you know how to use Google well, you can find, it's not hard actually to find the stochastic process which has exactly this guy as covariance. So here I suggest something. I suggest to take, so what do we want? We want a covariance between any odd difference to be 1 and even distance, sorry, any odd distance to be minus 1, and if any even distance to be 1, well then it's not hard to see that you just have to take this. I hope it's correct now. So I take any random variable with mean 0 and variance 1. Well then the covariance between xt and xt plus h, it's what? Well, it's going to be well, it depends on if, so it's going to be minus 1 to the power h times the expectation of n squared. Yeah. So that's actually nice and easy. So because is everybody okay with this? So because we have been smart, we don't really have to work, because if you're smart and if you think of this, then we get that this is the covariance of this process, therefore f of h is a covariance. If you're not smart, well, then you have to work. So we want to show that it is even. Well, that's okay. It clearly is an even function. And then we want to show that it's non-negative definite. So we want to show that, what do we have? We want to show that for all a1 to, for all n, for all a1 to an, and for all t1 to tn, what? Well, a1 to an multiplied by f of ti minus tj for 1 less than I, j less than n, multiplied by a1 to an. We want to show that this is positive. That's okay for everybody? And okay, well, let's have a look. So what's that? Well, that's some a multiplied by what? Well, okay, so I think this is where Clara, your first non-trivial question occurs. So I claim something. I claim that it is enough to check what? Well, to check that this is true for ti's of the form something plus I. So I just look at consecutive indices, in which case my matrix becomes so that my matrix becomes, well, we have the vector A which doesn't move, and then we have f of 0 which is then 1, then f of 1 which is minus 1, and then so on. So I claim that we only have to look at consecutive indices. Why? Well, because if they're not consecutive, it's just going to be... So, Clara, your question was, why is it enough to only take consecutive indices? Am I correct?
Yeah, it is.
Now, all of you who are following wake up and agree or disagree with me. If they are not consecutive, so let's suppose that we have, let's look at the sequence. So we take n is equal to 4, and I take 1, and then 7, and then 9. Okay, I'm just looking at an example. Well, this guy, I can consider him to be a subsequence of 1, 2, 3, 4, 5, 6, 7, 8, 9. But in my vectors here, I take only zeros corresponding to 2 to 3 to 6, and then 0 for 8. And then same thing here. So if I'm able to show that this is positive for any A, well then in particular it will also be positive for any combination which only takes non-consecutive indices. You see that?
Sorry, could you perhaps repeat it once more?
Yes. So if we have this guy with if we only have indices 1, 7, 9, then what you're really having would be A times gamma of 1, 1, gamma of 1, 7, gamma of 1, 9, gamma of 7, 7, gamma of 7, 9, gamma of 9, 9. Okay, so we have this. Sorry, it's n equals 3. And then we have A. So what I'm saying now is that this thing here is the same as, I put a tilde, and then I take gamma of 1, 1, gamma of 1, 2, up to gamma of 1, 9, gamma of 2, 2. My writing is really hard, but I'm very, very sorry. And then we go on up to gamma of 9, 9, like this. A tilde, where A tilde is what? It's going to be A1, 0, 0, 0, A7, 0, 8, and then A9. So I can see this computation here as a particular case of this computation here with a vector which has zeros at the components which are not taken into account. Yes?
Yeah, I see.
Therefore,
this is in fact true in general. It's not just in this specific example, right?
No, it's true in general.
Yeah.
So in fact, it's sufficient to work it out for consecutive indices, and then we will get it for any combination of indices.
Okay, that's useful.
Okay. So your question was wonderful. It was something that I was skipping over, but it's it's something that, well, when you look at what you're doing, it's actually clear, but it's good that I say it. Does everybody follow this argument?
Yes.
Okay. So now it's sufficient to check this. And I remember that I suffered a bit to do this, but let's have a look. Typically when I'm in a situation like this, I have an expression that's very, very ugly. I'm typically not I don't consider myself to be extremely smart, so when I don't have an idea, I don't have genius coming up to me, so I just take examples, and I take as many examples as I can until I have intuition that comes. So I can fill in a lot of pages of computations. So here I take n is equal to 1, and look at what happens, and it's true for n is equal to 1 because if n is equal to, well, wait first, what is this? Is this clear? Is that clear? Yeah, it is. So I have aj times plus or minus 1s, and it's going to be plus 1 if I plus j is positive, is even, and minus 1 if I plus j is odd. So I think this is clear. That's clear for everybody? Okay. And then I just take examples. So when n is equal to 1, I have 1, 1, so that's always positive. When n is equal to 2, I have this expression here, which is a square. When n is equal to 3, I have this expression here, which is a square. And therefore I'm left with, in fact, I guess it's easy to show that this is always a perfect square, and then it's always positive. I want to be convinced. You're convinced?
Why do you put a square? How do we come from the sum of ai minus 1 exponent I plus g to the square?
So my argument is it's true for 1, 2, and 3, so it's true in general. That's how I got here. If you want to check it for real, I think you have to be a bit more careful. So either you do it by recursion, which I hate, so I don't do that. Or what I would do is I would plug it into Mathematica for a few examples and see if it works. And another way would be to actually be smart. So it's going to be what? It's going to be this is going to be what? It's going to be a. So when I is equal to 1, so it's going to be a1 minus a2 . I think we can write it like this. So I guess what I'm saying is that this expression here is the same as this expression, this multiplied by this. And yeah, I guess you just have to work it out. You have to work out this guy explicitly. So this guy is going to be what? It's going to be the sum of all the AIs times 1 plus all the off diagonal components. So all the AIs times 8. Yeah, it's actually clear. It's actually easy. I'll do it. So where am I? On an exercise, still the same exercise. So if I look at this sum here, but typically all these things are easy to prove once you see them. The hard part is to see them. So how did I see it? Well, you see, I extrapolated from here, like this, and then I just extrapolated. So what's this sum going to be? It's going to be the sum of all the AI squared plus the sum for I different from j of the AI aj minus 1 to the power I minus 1 times minus 1 to the power j minus 1, which is what? Well, it's just the... So yeah, here it's obvious. And this minus 2 can disappear because it's always plus 1. Yeah, so it's obvious.
Thank you.
So, but I don't know who I'm talking to, but so the hard part is, typically it's not hard to prove once you have the result, but the hard part is guessing the result. So here I just guessed from here that was the correct expression, but I'm pretty sure I never checked. Okay. God, I'm slow. 4:15. Are we happy with this exercise B? Clara, did I answer all your questions?
Yes, perfect. Thank you.
Okay. So the C, question C. So what was the guy here? So in question C, the function that you have is 1 if h is 0, 0.4 if h is plus or minus 1. Sorry, I can't. I've been staring at my iPad since this morning, since 9 this morning, so it's getting... I think in 6 months I'll just be walking around like this. So 0.4 and then 0 otherwise. Okay. So what I say is that so I remember trying it out last year and I didn't find an easy way to show that this function was non-negative definite. So I didn't see any neat recursion. I saw nothing. So I wasn't able to do it directly. So then I was left with trying to find a process which has this kind of function as covariance. And well, luckily for me, I had pre-prepared the work in the course notes, because on page 35 of chapter 1, I hope it's the correct page. Yes, it's the correct page. So in page 35 of chapter 1, what we saw is that this guy here is the autocovariance function of a moving average of order 1 if and only if the difference between this term here and this term here is less than 1/2. But that's the case here. That's the case here because 0.4 divided by 1 is less than 1/2. Okay. So we are left with what? We are left with the fact that we have a covariance process, and then the game is to write it out explicitly. Sorry, no, we don't have it. We have a stochastic process, and then the game is to work out the process explicitly. So what I say is that we take, we can have two of these guys. Theta 1 and theta 2 has to be of this form, where rho 1 is 0.4. So what do? I just take the expression. So I think I'm arriving at another one of your questions, Clara. I think, again, very good question. So we have this. We have rho 1, which is equal to 0.4, so that this gives us theta 1 and 2, which are equal to, well, either 0. I suppose I didn't make a mistake here, so it's either 2 or 1/2. I guess I didn't make a mistake. And then what? Well, then so then sigma squared times 1 plus, so if theta is equal to 2, well, it should be theta 1 actually. If theta 1 is equal to 2, then I have sigma squared times 1 plus 4, which has to be equal to 1, and sigma squared times 2, which has to be equal to 0.4. So it tells me that sigma squared is equal to 0.2, I guess, and theta is equal to 2, so that my process is xt is equal to zt plus 2 zt minus 1, and the zt's are iid, which means 0 and variance 0.2. So I think that was your remark, Clara, that I was forgetting, and I completely agree with you. I was forgetting to specify the sigma squared in terms of the theta in my correction.
I'm still a little confused because if we evaluate f at 0, shouldn't it be the variance normally?
Yes, it is the variance. It's the variance of the process, not the variance of the noise. So the variance of the process, it's on page 34. So recall chapter 1, page 34. Or you do it again. If your process is xt is of the form zt plus theta times zt minus 1, well then the covariance of this guy is sigma squared, I'm sorry, the zt are iid, which means 0 and variance sigma squared. Then the covariance of this guy is sigma squared times 1 plus theta squared, sigma squared theta, and 0.
Yeah, and it's fine.
Sorry, and then h is larger than 2. So what's a bit disturbing here is that this guy is 1. Well, this 1 is in fact the covariance, but because theta is equal to 2, then sigma squared needs to be equal to 0.2. Okay.
Yeah, I agree.
Yeah, and then that's, I guess that was what you were saying very kindly. But yes, this is wrong. I mean, I cannot leave the sigma squared unspecified. The sigma squared depends on the choice of theta. So if theta is 2, sigma squared is 0.2 unless I made a mistake. And if theta is 1/2, well then sigma squared times 1 plus, I have no memory, times 1 plus 1/4 is going to be equal to 1, and sigma squared times 1/2 is going to be equal to 1, so sigma squared has to be equal to 2, and therefore we have another solution. So that's the first solution, and the other solution is xt is zt plus 1/2 of zt minus 1, but zt riid would mean 0 and variance 2. And these two guys are indistinguishable. They are basically the same, but they are different processes with the same covariance structure. Okay for everybody? Okay. The next one. So the previous argument. So now we have row 1, which is 0.9. Yeah, so the difference now is 0.9. So we cannot apply the result from from the course, because the result from the course only applies if row 1 is less than 0.5. Therefore, the function is not the ACF of moving average process of the form given by example 1.39, but that does not mean that it's not the autocovariance function of some other process, at least not for the moment. So we have to check that this function is not non-negative definite, and the only, well, at least the only way that I found to check that it's not non-negative definite is to find an example of a vector which, when you multiply it to the left and to the right, gives you something negative. That's the only example I found. That's the only way I found, and then in order to find an example, well, you just have to play around, and I found, I hope it's correct, that if you put minus 1, 1, minus 1 here, then you get something which is negative, therefore it's not non-negative definite. How did I find this guy? Can't remember, I just found him.
Yeah, excuse me, it was my question actually. I didn't get why you choose.
Okay, so I remembered having a question about this. So I literally can't explain how I found this vector. So typically what I do when I get, I mean, I don't do this often. I'm not masochistic, but if I have something like this, so I have 1, 0.90, 0.910, 0, 0.91, then I just plug in values, and then I just look at what it looks like. So we have what? We have x plus 0.9 y. Well, I actually know what it's going to be. What this is going to be? It's going to be x. It's going to be x squared plus y squared plus z squared plus twice 0.9 xy plus xz plus yz. I think that's what it's going to be. So I'm going to get 0.9 times Does this look okay? And then you just just try out values of x, y, and z, and it's a habit of a math student is to look for the simplest examples, so I take versions of this. I look for values of plus or minus 1 to make the thing break down. And then that's how I got to this 1 minus, well, that's how I got to this guy here. I'm afraid I can't help you really much more. I don't have any. There's no specific general recipe which will work in every case. Okay.
Okay, thank you.
Well, it's a disappointing answer, but that's my answer. And then there's the generalization for general row 1. Is that it? Where's my... Yeah, so there's a generalization for all alpha, and I ask you to show that it's if alpha is larger than 1/2, it just doesn't work. So sorry, the number E is when it's 0.6. Yeah, so for 0.6, what you notice, well, if you're playing around with this thing, what you realize is that it's harder to get it to break down. And the way I found to make it break down was to use a larger matrix. And then, well, I just generalized this to this guy here. And then I got, with this guy here, I got a negative number.
I have a question.
Yes?
Why did you change the vector after the equality? Because it is 1 minus 1, 1 minus 1, and after it is minus 1, 1 minus 1, 1.
And that's most certainly a typo.
Okay.
Because I think this result should be positive, the
Yes.
example you gave. No, I'm not sure.
Yes, I tried it. Normally it's positive.
Nah, you're lying.
No.
I'm going to use my authority here and say you're wrong. Well, I think we all get the idea. So I believe you. I sincerely believe you that this is wrong. I think we all get the idea. I must admit I didn't try it out. So I saw. I think it was again Clara's question. I didn't try it out, so I'll use I'll abuse of my authority and say, well, good luck, all of you. Find one. If this is wrong, then there must be another one, because
Okay.
the result is certainly true. Is this not correct, Clara? You had a long discussion, and I thought I was agreeing with myself, but then you disagreed with me.
Well, I'm confused with the D. What does a D represent here?
Okay, so I looked at your question here, and I think I convinced myself that I was right, but that doesn't mean I'm right, of course. It just means I convinced myself. So how did I do it? We take the general structure of the matrix. It's going to be 1 alpha 0 0. Okay, so sorry, I'll try, and then we'll take a break because I'm getting less and less coherent. What I realized when playing with these guys is that the closer you were getting to 0.5, the harder it was to get a counterexample, so the larger the matrix you needed to take. That was my intuition anyway. So I'm going to take a matrix of size D, of this form. Okay, and I'm taking it of size D, like this. And then my intuition is that I'm going to take vectors of, I think I wrote it down somewhere. Yeah. I'm going to take vectors of this form, x1, x2, x3, up to xd. And in here it's going to be x1, x2, x3, up to xd. And then I'm just going to try and work out what this looks like. Please stop me if I make a mistake. Alpha xd minus 1 plus xd. I think that's it. And then I have what? I have x1 squared plus alpha x1 x2, so that's an alpha, plus x alpha x2 x1 plus x2 squared plus alpha x2 x3, and so on up to alpha xd minus 1 plus xd squared. And I think, if I'm not mistaken, this looks in general like sum of the xj squared plus 2 times, yeah, I seem to be agreeing with myself, 2 times alpha times the sum of ai different from j xi xj. So here, unless I made a mistake, which is intensely possible, I worked out all these expressions for all sizes of the matrix. That's okay? And then the game is, can I find, in terms of alpha, can I find xi's and xj's which will make this negative? And as far as I understand, if I take xi's to be plus or minus 1, then this will become what? It's going to become d. So the first term, this guy here, is just d because it's a sum of minus or plus 1 squared. And then I'm left with what? With then plus 2 alpha times what? Well, times 1s plus minus 1s, depending on how many 1s and how many minus 1s there are. Is that okay? So if I have 4 plus 1s and 4 minus 1s, I'll have 0 here. If I have 7 plus 1s and 3 minus 1s, I'll have 4, and so on. That's okay? I guess it is. And then what? Well, if alpha is positive, then I'm going to take xi to be minus 1 to the power I plus 1. Sounds good. So that I'm left with d plus d plus what? I don't know. So it's going to be plus 2 alpha times 1 plus... no, I'm talking rubbish. It's, and you're not saying anything, so maybe just... Yeah, I don't want to work this out. I just want to work it, I just want to leave it like this. So alpha times the sum of the xi, xj's. So then if I have these guys here which are alternating in sign, then this is going to be just a sum of so it's d, so yeah.
Yes. For the sum over the I and j,
Yeah.
My intuition is that we do not sum over all the I and j's. We just may have xi and xi plus 1 and maybe xi minus 1 together, because it won't.
Yeah, you're right.
So maybe it will ease your sum.
Yeah, so we have yeah, for x1 we have x2 and x, yeah, so you're right, it's I going from 1 to d minus 1 like this. You're very right.
And so this product is always -1
Yeah.
if the sign alternates.
Yeah, thank you. You're saving me. So then we get d minus 2. Is that correct? With a minus. So if alpha is positive, then we just have to take d. No, it's not d minus 2, it's d minus 1. And there. So if alpha is positive, then we have to take d large enough to make this this negative. And if alpha is negative, then I don't know. Exercise. I realized that I didn't do the case alpha negative here in my notes. Is that okay for everybody? So do you see do you understand the game? So I'm not finished, but it's already 20 to 5, and I'm in exercise 4. So I think Clara and Roland, I count on you to agree or disagree with me. I think that this covers the case where alpha is larger than 1/2. And the case where alpha is less than -1/2, it's not covered here, but you have to find another combination of xi's which will do the job. That's okay?
I agree with you, I think, because I had the same formula, but I used n instead of d. But I think the problem that confused me was just that in the correction where you wrote your matrix, the last term was -1 to the exponent d. Well, I think it should be d minus 1 or d plus 1 because we start with 1 minus 1 exponent 0 and not exponent 1.
Very, very, very good remark. Thank you. You are slowly but surely earning your place in the acknowledgements to this book. Thank you. So, for those of you who are sleeping, why did I not finish the exercise? Because I'm tired. That's all. I let you do it. If you find a solution, please send it to me. Okay? Ferdinand, you have one.
Yes, I have a last question before to give you your break. It was in the sub-question C. When you compute sigma squared for theta is 1/2. If you could go up in your notes, it will help me. I'm not sure that 2 times 1 plus 1, 4 can be 1. And that here sigma squared equals 2 doesn't verify both equations, explicitly the first one.
So where's my mistake?
I don't know. I don't know if there is any sigma squared. I didn't have the general results in mind. If we must have a solution or not.
There must be. So if theta is 1/2, if theta is 1/2, then I have a solution here. Sorry, if rho is 0.4, then I have a solution. I guess that I'm correct. So 1/2 is correct, isn't it? Well, anyway, we know that the roots are we know that the roots are inverse one to the other, so if one of them is 2, then the other one is 1/2, and that's correct. Maybe I'll compute this in Mathematica.
So I don't know if the first one is 2 because if no, yes, sorry, never mind. It was rho 1 squared.
If anybody tried it out, please give us a shout. Yeah, so it is 2 and 1/2. Then if theta is 1/2, then I have to have sigma squared such that sigma squared theta is, yeah, but it's not 1 here. I'm being silly.
Oh yes, it was 0.
It's not 1 here. It's 0.4. So thanks for your remark, but I was just being silly here. And then I guess, is that okay? Because then sigma squared.
It should be so 0.8.
So sigma squared should be 0.8, and is
yeah, that much.
This is okay. Yeah, thanks. Very good remark. Anything else? Any questions on this?
Sorry, what was the last thing that has changed? I'm not sure.
No, it's just when I was doing the correction here, I was silly. And we were all collectively silly because I put a 1 here instead of putting the correct value, which is 0.4.
Yeah.
So then here it's not a 2, it's a 0.8. Okay, if there's no more remarks on this, then I suggest we take well, not too long break. So it's 20 to 5. Let's start again at 15 minutes, and then maybe I'll go a bit faster for the rest because it's yeah, I'm being a bit slow, and I would like to move on a bit in the course. Okay, so let's have a break. Again, thanks to all of you for asking your questions.